Empty space is a lie your eyes tell you. Look up on a clear night and the dark between the stars reads as nothing at all, a finished, quiet backdrop with the light switched off. But everything that shines, every star in every one of the 2 trillion galaxies we can see, adds up to less than 5% of what the universe is actually made of. The other 95% gives off no light, and we cannot see it, and in a few places we cannot even confirm it is safe. Drifting in that dark are billions of unlit worlds with no sun. Passing through our own solar system are visitors from other stars that we notice only as they leave. Threaded invisibly through your galaxy is a scaffold of matter no one has ever touched. Tonight we are going to count down 10 things scientists believe are lurking in that dark escalating from the merely hidden to the genuinely unsettling. And I will tell you now, before we start, that the most frightening thing on this entire list is not an object at all, and I'm going to make you wait for it. By the end of tonight, you will know exactly what it is. Get comfortable. If you are the kind of person who finds it calming to have your sense of the universe quietly rearranged, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this, the empty sky is going to feel less like an empty room, and more like a crowded one with the lights left off. Now, let's gently drift into this. The night sky lies to you, and it lies by being calm. When you look up, or when you close your eyes and picture what is above the roof over your head, you see something quiet, a black field, a scatter of fixed points, a backdrop that does not move, does not change, and does not care. It feels finished, the way an empty room feels finished. And that feeling, that sense of a still and vacant dark, is one of the oldest and most comfortable mistakes the human mind makes. Because the dark is not empty. It is full. It is more crowded, more active, and more strange than any lit room you have ever stood in. And the reason it looks empty is not that there is nothing there. The reason it looks empty is that almost nothing there gives off light. Your eyes evolved to catch a narrow ribbon of the electromagnetic spectrum, a thin band of visible colour, and everything that lives outside that ribbon is, to you, simply not there. You're standing at a window that shows you less than 1% of the view and calling the rest of it darkness. Tonight we're going to count our way through 10 of the things hiding on the other side of that window. 10 things that scientists have found or inferred or been forced to take seriously that are lurking in what looks like empty space. Some of them are objects. Some of them are not objects at all, but regions of nothing, or states of matter, or properties of space itself. What they share is that you cannot see them. Some emit no light. Some are defined entirely by absence. Some have never been directly detected even once, and by their nature might only announce themselves at the exact moment they arrive. I want to be honest with you about the shape of this list, because the honesty is part of what makes it land. We are going to start small, or at least start close. The first few things on this list are the kind of thing you could, in principle, bump into. Worlds, visitors, objects with edges, and then, one rung at a time, the ground is going to tilt. The things are going to get larger and less like objects, and harder to point at, until by the end we're no longer talking about something in space at all. We will be talking about space. Because the most frightening thing on this list, the thing sitting at number 1, is not a rogue world or a wandering monster or a beam of radiation. It is a possibility about the ground state of reality, and it is the reason I want you to stay with me all the way to the end. I am not going to answer it early. I am going to make you wait for it, the way the universe is making all of us wait for it, and when we get there, I think you will understand why it belongs at the top. None of this is meant to frighten you into staying awake. That is the strange thing about a list like this. The feeling I am after is not fear. It is something quieter and I think better, a kind of slow readjustment of where you thought you lived. You did not grow up in a calm, empty, finished universe with a few lights turned on in it. You grew up inside a mostly invisible one, embedded in it, made of the same hidden material as the things we're about to discuss, and you never noticed because the part you can see is the part that shines. Tonight we are going to talk about the part that does not. Consider, before we begin, how thoroughly the visible fools us. Every star you can pick out with the naked eye belongs to our own galaxy, and there are only a few thousand of them within reach of a dark-adapted human eye. Our galaxy holds somewhere between 100 billion and 400 billion stars. Beyond it lie something like 2 trillion galaxies in the observable universe alone, and even that unthinkable senses of light, every star in every one of those 2 trillion galaxies, adds up to less than 5% of what the universe is actually made of. 5%. Everything that shines, everything that has ever shined, every sun and every quasar and every burning thing in the sky, is the thin, bright skin on top of something overwhelmingly dark. The other 95% is the subject of the last 2 items on this list, and we do not know what it is. So when I say the dark is not empty, I am not being poetic. I am giving you the plain arithmetic of the situation. The universe is a place where the things that matter most, the things that hold galaxies together and decide how everything ends, are precisely the things that give off no light and let no telescope find them directly. We live inside a mystery that is mostly opaque to us, and we have spent a few centuries learning to detect the edges of what we cannot see, one clever indirect trick at a time. That is really what this list is. It is 10 places where the darkness stopped being empty under careful examination. 10 times someone pointed an instrument at what looked like nothing and found that the nothing was doing something. And in almost every case, the honest scientific position at the end is not a tidy answer. It is a carefully worded version of we do not know, sometimes we cannot yet know, and occasionally we may never know. Those are not failures. Sitting comfortably with an unanswered question is, I would argue, the most grown-up thing a curious mind can learn to do, and by the end of tonight you will have 10 of them to sit with. It is worth pausing on how we ever learned any of this, given that we are so badly equipped for it. Every animal on Earth, including us, evolved senses tuned to survival on the surface of one small planet, and none of those senses were built to perceive the universe as it really is. Your eyes catch visible light because visible light is what filters down through the atmosphere and bounces off the things that mattered to your ancestors, predators and prey and ripe fruit and running water. They were never meant to show you a rogue planet, or a gravitational wave, or the state of the vacuum. And so every single thing on this list was found not by looking harder with the eyes we were born with, but by building new senses from scratch. Infrared cameras that see heat, radio dishes that catch wavelengths longer than a house, detectors buried in mountains waiting for a particle that almost never interacts with anything, arrays of dead stars timed to the billionth of a second. We are a species that noticed how little we could perceive, and then, patiently, over a few centuries built the organs we were missing. There is a real humility in that, and I want to keep it beside us the whole way down this list, because it changes the emotional colour of everything. When I say we cannot see these things, I do not mean we failed. I mean the opposite. I mean that the only reason we know they are there at all is that we understood our own blindness well enough to work around it. Nearly everything on this list was discovered indirectly, by inference, by watching the effect a thing has on something we can see, rather than by seeing the thing itself. That is not a weakness in the science. It is the entire method. You learn to read the dark not by staring into it harder, but by watching what it does to the light at its edges. We begin close to home, not in some far galaxy, but in the space between the stars of our own, in the gaps we assume are empty because nothing is shining there. Because it turns out those gaps are not empty either. They are populated in numbers nobody predicted by worlds that will never see a sunrise. Let us start there, with number 10, and with a photograph taken in 2023 that quietly rewrote how many planets the galaxy is allowed to have. In October of 2023, 2 astronomers pointed the James Webb Space Telescope at the heart of the Orion Nebula, which is one of the most photographed, most studied, most familiar patches of sky in the entire catalogue of astronomy. Orion is the nursery. It is where we go to watch stars being born, a glowing cloud about 1,300 light-years away that generations of telescopes have stared into. Samuel Pearson and Mark McCaurin of the European Space Agency were looking into the dense central cluster, the little knot of bright young stars called the trapezium, and they found something in the spaces between the stars that should not have been there in the numbers they saw. They found worlds, free-floating planet-sized bodies, bound to no star at all, not orbiting anything, not warmed by anything, just drifting through the nebula on their own. And there were not a few of them. There were roughly 540, objects ranging from about twice the mass of Saturn up to about 13 times the mass of Jupiter, hanging in the dark with no sun to call their own. We had known rogue planets could exist. The idea was old and reasonable. When a young solar system forms, it is a chaotic, violent place, a shooting gallery of forming worlds tugging on each other, and the theory said that every so often one of them would get flung out, gravitationally ejected, kicked loose from its family and sent wandering into interstellar space, a lonely exile. A few here, a few there, the occasional orphan. That was the picture. What nobody predicted was the sheer abundance, the idea that if you looked into one ordinary star-forming cloud, you would find hundreds of them at once, as if the galaxy were producing unlit worlds, not as rare accidents, but as a routine byproduct. And then it got stranger, because some of these rogue worlds were not alone. About 40 of them were found in pairs, 2 planet-mass objects gently orbiting each other with no star anywhere in the arrangement. Pearson and McCaughrean gave them a name that has stuck. They called them Jupiter-mass binary objects, or jumbos. Roughly 9% of the free-floating objects were in these pairs, and a few were even in threes. This is the part where the textbooks fall quiet, because our theories of how stars and planets form do not have a good way to make a jumbo. You can just about explain a single ejected planet. You cannot easily explain how you get so many planet-sized objects forming independently of any star, and you especially cannot explain how 2 of them ended up softly bound to each other, instead of being scattered in random directions by whatever threw them out. Ejection is a violent process. It should fling things apart, not leave them holding hands. Both the abundance and the pairing are at the moment unaccounted for. When scientists find something a theory forbids, that is not a nuisance. That is the sound of a door opening, and right now nobody is sure what is on the other side of it. Here is what makes these nomads genuinely unsettling rather than just puzzling. They produce essentially no light. A planet does not shine on its own, and these have no sun to reflect. You cannot see them the way you see a star. We found them only because the James Webb Telescope is sensitive to infrared, to heat, and these young objects still glow faintly with the warmth of their own formation. An older, colder, rogue planet, one that has been drifting for billions of years, would be almost perfectly invisible. The only way to catch one of those is to wait for it to pass directly in front of a distant star and bend that star's light for a moment with its gravity, a fleeting trick of alignment called microlensing that shows you the object existed only after it has already moved on. Now put those 2 facts together, the invisibility and the abundance, and follow them out to their conclusion. Current estimates suggest there could be billions of rogue planets adrift in the Milky Way. Not millions, billions, potentially rivaling or even outnumbering the stars themselves, which means the space between the stars, the part of the sky we have always treated as the emptiest, most nothing part of all, may be quietly populated by more worlds than there are suns. And we have no catalogue of them. We do not know their positions. We do not know their trajectories. We do not know their numbers except as a rough guess. There could be one drifting through the outer reaches of our own solar system right now, out past the planets in the cold dark, and we would have no way of knowing it was there. Let me take you to the surface of one of these worlds, because I think it is the only way to really feel what we're talking about. You are standing on the night side of a rogue planet, except that calling it the night side is a mistake, because there is no other side. There is no day here. There has never been a day here, and there never will be. There is no sun in the sky, no warm point of light climbing toward a horizon, no dawn coming. Above you, the stars are perfect. There is no glare from any nearby sun to wash them out, so the whole field of the galaxy hangs overhead, unblinking, sharper than any sky you have ever seen from Earth. It is the clearest view in the universe, and there is no one to see it. And under your feet, faintly, there is warmth, not from above, from below. Because a planet like this, if it is massive enough, can hold on to the heat generated by the slow, radioactive decay of the atoms far inside it. The same kind of internal heat that keeps the inside of the Earth molten, and it can hold that heat for billions of years. Some scientists, including work associated with the astronomer Dimitar Sasolov, have pointed out that such a world could keep an ocean of liquid water beneath a thick shell of ice, warmed entirely from within. No star required, no sunlight required, just chemistry and pressure and time in a place that will never have a morning. I am not telling you there is life down there. I am telling you that we cannot rule it out, and that the galaxy may be full of these dark, self-heated, ocean-bearing worlds, moving in silence, and that not one of them has ever been visible to us until it happened to drift across the light of a more distant sun. Billions of worlds, most of them we will never see, some of them perhaps not entirely dead. Consider how strange the detection method is, because it tells you a great deal about how hidden these worlds are. Microlensing works like this. A rogue planet, drifting through space, happens to pass almost exactly between us and a much more distant background star. Its gravity bends the light of that star, acting like a lens, and for a brief window, hours or days, the distant star appears to brighten and then fade in a very particular, predictable pattern. That flicker is the only evidence you get. You never see the planet. You see a distant star momentarily brighten because something invisible crossed in front of it, and from the exact shape of that brightening you can work out the mass of the thing that caused it. The object itself remains completely dark. It reveals itself only by what it does to the light of something behind it, and then it is gone, having moved on, unlikely ever to line up with that particular star again. We are quite literally cataloguing these worlds by their shadows, or more precisely by the way they magnify the light around them, and only in the rare instance when the geometry lines up. Now think about the scale of the loneliness involved, because this is where the numbers do something to you. The nearest star to our Sun is a little over 4 light-years away, which is a distance so large that if you shrank the Sun to the size of a grain of sand, that neighbour would still be miles away across an otherwise empty city. The space between stars is overwhelmingly, almost perfectly empty by the standards of anything we experience. And it is into that emptiness that these rogue worlds are scattered, each one, on average, unthinkably far from any other object, drifting through a cold and lightless expanse for billions of years at a stretch. A rogue planet does not have neighbours in any meaningful sense. It has a sky full of distant, uncaring stars and an eternity of dark between it and everything else. If there is an ocean beneath its ice, warmed from within, then that ocean has been sealed away from the rest of the universe since before our Sun was born, a private world with no window, moving through the dark on a journey with no destination. And here is the detail that genuinely unsettles the theorists, the one I keep coming back to. In 2024, a follow-up study found that at least one of these Jupiter mass binary objects was giving off radio waves, blazing with radio emission that our models of planet-sized objects simply do not predict. We expect radio emission from stars, from objects with powerful magnetic fields and energetic processes driving them. We do not expect it from a cold pair of starless planets drifting in the dark. So not only can we not explain how these objects formed, or how they paired up, we now cannot fully explain what some of them are doing. Every answer we get from the Orion Nebula seems to arrive with a new question attached. And the honest state of the field right now is that we found hundreds of worlds where our theories said there should be almost none, and we do not yet know what they're telling us. But a rogue planet at least formed here, in our galaxy, out of the same material as everything else. The next thing on the list did not. The next thing came from somewhere else entirely, crossed an unthinkable distance of empty space, and passed straight through our own solar system while we watched, too late and unable to do anything but wave as it left. For almost the entire history of astronomy, we assumed that everything we saw moving through our solar system belonged to it. Comets, asteroids, the planets themselves, the whole moving cast of the sky was born here, from the same disk of gas and dust that made the Sun, and it stayed here, bound to the Sun by gravity and long loyal orbits. The solar system was a closed household. Nothing came in from outside, and nothing left. That assumption held right up until October of 2017, and then a single point of light broke it forever. The object was named Oumuamua, and it was the first thing we had ever seen that did not belong to us. We could tell because of its path. Everything gravitationally bound to the Sun travels on a closed orbit, an ellipse, a loop that comes back around. Oumuamua was not on a loop. It was on a hyperbola, an open path, coming in from the depths of interstellar space, whipping around the Sun once, and leaving again forever, never to return. Its speed and its trajectory made the conclusion unavoidable. This thing had been drifting between the stars for how long nobody knows, possibly hundreds of millions of years, and its long, cold journey had happened to intersect our little corner of the galaxy at the exact moment we had telescopes capable of catching it. We got a few weeks with it. That was all. By the time it was discovered, it was already on its way out, already fading, and the world's telescopes swung around to grab whatever data they could before it slipped beyond reach. What they got was strange enough to start an argument that is still going. Oumuamua was oddly shaped, elongated, tumbling, and it showed a small acceleration as it left, a tiny extra push that could not be fully explained by the visible jets of gas you would expect from an ordinary comet warming in the sunlight. That little unexplained nudge was enough to launch 1,000 headlines, and we will come back to what people made of it, because it is one of the 2 places on this list where the science brushes up against a much wilder idea. Then, in 2019, we found the second one, Comet Borisov, another interstellar visitor, this one behaving much more like a normal comet, with a tail and a coma of gas, but again on an open, unbound, hyperbolic path. Again, a thing from another star system passing through and leaving. 2 visitors in 2 years, after thousands of years of seeing none. And that raised a quiet, uncomfortable question. Were these things rare, or had they always been streaming through, and we simply never had eyes good enough to notice? The answer arrived on the 1st of July 2025, when a survey telescope in Chile, part of a network called Atlas, caught a third one. It was confirmed almost immediately, announced by the Minor Planet Center the very next day, and given the designation that marks it as the third interstellar object ever confirmed. Its formal name is 3I Atlas, and as a comet it also carries the label C2025N1. And this one was different again because this one was moving fast, on the most extreme path of all 3. Let me give you the numbers, because the numbers are the story here. An orbit's eccentricity tells you how open or closed it is. A perfect circle has an eccentricity of 0. Anything below 1 is a closed, bound orbit, a loop. Anything above 1 is open, unbound, a one-way trip. Oumuamua's eccentricity was just above 1. 3I Atlas came screaming in with an eccentricity of about 6.14, which is enormously more hyperbolic, the signature of an object that was moving very fast relative to the Sun before it ever arrived. It came in almost edge-on to the plane of the planets, on a backward retrograde path, dipped inside the orbit of Mars, and swung around the Sun at the end of October 2025, passing closest at a distance of about 1.36 times the distance from the Earth to the Sun. And then, like the 2 before it began to leave, outbound now, heading off toward a distant meeting with Jupiter, and after that, back into the interstellar dark it came from. It is worth pausing on the journey each of these objects made to reach us, because the distances involved dwarf anything in human experience. An interstellar object does not come from a neighbouring town or a neighbouring planet. It comes from another star, and the nearest stars are light years away, meaning the object has been travelling through the empty dark between suns for a length of time that likely runs into the hundreds of millions of years, drifting cold and dark and alone, having been flung out of its home system long before there were humans, or mammals, or possibly even complex life on Earth. It carried whatever it was made of, the ice and rock of a planetary system we will never see, across a gulf so wide that light itself takes years to cross it, and its entire passage through our solar system, the only part of that endless journey we witnessed, lasted a matter of weeks. We caught the last few pages of a story hundreds of millions of years long, and then the book closed and drifted back into the dark. And each of the 3 has been just different enough to keep us honest about how little we know. Oumuamua was dry, oddly shaped, and showed that faint, unexplained push. Borisov was a textbook comet, wet and gassy and almost reassuringly normal, as if to prove the first one was not a fluke. And 3I Atlas came in faster, and on a more extreme path than either, behaving like a comet but arriving with a velocity that speaks of a long, fast fall from somewhere far away. 3 objects, 3 personalities, 3 fragments of 3 alien systems, and from that tiny sample we are trying to reconstruct what the debris of the whole galaxy is like. It is a little like trying to describe every ocean on Earth from 3 bottles washed up on a beach, except the bottles came from other worlds. Here is the thing that should make the back of your neck prickle. We did not see any of these coming. In all 3 cases we detected the object only after it was already inside the solar system, usually already past its closest approach, already on its way out. We have no early warning system for interstellar visitors. We have no census of how many pass through in a given year. We get at best a few days or a few weeks of frantic observation before the thing recedes beyond the reach of our instruments, and then it is gone, and we are left with a scatter of measurements and a lot of open questions about what it was made of and where it came from. 3 objects in 8 years, and each one a stranger we met only in passing, on its way out the door. Now, I want to be careful and clear here, because this is exactly the kind of topic where the truth is quieter than the rumour. The overwhelmingly likely explanation for all three of these visitors is completely natural, and honestly, it is a lovely idea in its own right. Every young solar system as it forms flings out debris. Comets and chunks of rock and ice that got too close to a forming giant planet and were slingshotted into interstellar space, exiles from other stars, exactly the way we think rogue planets are made, just smaller. The galaxy should be full of this stuff, an enormous slow drift of cast-off material from billions of other planetary systems, crisscrossing the space between the stars. Under that picture, the reason we suddenly started finding interstellar objects in 2017 is not that they arrived. It is that our sky surveys finally got sensitive enough to catch them, and if that is right, then the ones we've found are not rare at all. They are the first three we happened to notice, and the new generation of survey telescopes now coming online is expected to find many, many more. So the horror here, if you want to call it that, is not that something dangerous is out there. It is the quieter realization that our own neighborhood, the solar system we think of as ours, our closed and private household, is actually a public thoroughfare. Things from other stars pass through it, and we do not guard it, and we do not track it, and until very recently we did not even know it was happening. For a few days each, 3 objects that were born around alien suns, that formed in planetary systems we will never visit, slid silently through the space we live in, and we found each of them only in the act of leaving. And we have no idea how many others have crossed through unseen, in the years and centuries and millennia before our telescopes were ready, drifting past a sleeping Earth and out the other side. Now, I have to talk about the wilder idea, because this is one of the 2 places on this list where a genuine scientific mystery has attracted a much louder, much stranger claim, and I promised you honesty in both directions. Ever since Oumuamua, and now with 3i Atlas, a handful of voices, most prominently the Harvard astronomer Avi Loeb, have raised the possibility that an interstellar object might not be natural at all, that it might be an artifact, a piece of technology from another civilization, a probe, a fragment of a craft, something made rather than something formed. The argument usually leans on the odd details, Oumuamua's strange elongated shape and its small unexplained acceleration, and on the general point that if we only ever catch these things on their way out, we might be missing evidence of design. I want to treat that idea with respect and then tell you honestly where the weight of the evidence sits, because both halves matter. The respectful part is this. It is not a crazy question to ask. We have found exactly 3 of these objects. We have studied each of them for only days or weeks, and our data on all 3 is thin. In that situation, keeping an open mind about what they could be is good science, not bad science. But the honest part is that natural explanations account for what we have seen without needing to invoke anyone building anything. Oumuamua's acceleration is most likely explained by ordinary outgassing, the gentle push a comet gets as ice turns to gas in the sunlight, even when that outgassing is too faint to see directly. Its strange shape is unusual, but not impossible for a natural body. And the sensational headlines you may have seen about 3i Atlas changing course, or behaving in ways that suggest steering, generally describe exactly this same ordinary process, the small, expected, entirely natural nudge that comes from a comet venting gas as it warms near the sun. It is not steering. It is a comet doing what comets do. The overwhelming scientific consensus is that all 3 interlopers are natural objects, and that the truth, a slow drift of cast-off debris from billions of other star systems crisscrossing the galaxy, is strange and wonderful enough without adding anything invented on top of it. And the scale of the arithmetic supports the natural picture in a way that is genuinely humbling. If the galaxy really is full of ejected material from other planetary systems, then interstellar objects should be passing through the inner solar system all the time, most of them small, dark, and far too faint for our current telescopes to catch. The 3 we have found are almost certainly just the largest or nearest or luckiest of an enormous, mostly invisible population. That is why the new generation of survey telescopes now coming online matters so much. They are expected to catch these visitors by the dozens, perhaps eventually by the hundreds, and when they do, we will finally learn how crowded our own doorstep has always been. The unsettling thing was never that one of them might be a spaceship. The unsettling thing is that our quiet private solar system has been a public crossing all along, and we're only now building the eyes to see the traffic. That is the last of the things on this list that are, unmistakably, objects, worlds and visitors, things with surfaces and edges, things you could in principle stand on or fly past. From here on, the list starts to change, because the next thing was here before any of them. It is not a visitor, and it is not a wanderer from another star. It was made in the first fraction of a second of the universe itself. It has no surface and no light and no address, and there may be one passing through the ground beneath you right now. In 1974, two physicists, Bernard Carr and Stephen Hawking, published an idea about the very beginning of the universe that has been quietly haunting cosmology ever since. Their idea was this. When we talk about black holes, we usually mean the corpses of massive stars, objects that formed when a giant sun ran out of fuel and collapsed under its own weight. That is how black holes are made today. But Carr and Hawking asked a different question. What about the first instant of the universe, the first tiny fraction of a second after the Big Bang, when everything was compressed into a state of almost unimaginable density, and everything was violently uneven? In that chaos, they argued, you would not need a star. The raw material was already crushed so tightly that any region slightly denser than its surroundings could have collapsed directly into a black hole, right there, in the opening moment of time with no star involved at all. They called these objects primordial black holes, and the phrase does a lot of work. Primordial, from the beginning. Not the remains of something that lived and died, but a relic of creation itself, formed before there were stars, before there were atoms, in the first heartbeat of existence. And the truly interesting part of the idea is that, depending on their mass, some of them could still be here today, drifting through the universe, having survived every second of the last 13.8 billion years. Now, black holes are not eternal. Hawking himself showed that they slowly leak energy and evaporate over time, and the smaller they are, the faster they go. So the smallest primordial black holes, the ones formed with tiny masses, would have evaporated away long ago, dying in a final flash. But there is a threshold. Above a certain mass, a primordial black hole would have survived intact to the present day, and here is where the idea connects to one of the biggest mysteries in all of science. Because these surviving relics are one of the leading candidates to explain dark matter. Let me remind you what dark matter is, because it matters for the next several minutes, and for the whole back half of this list. When astronomers measure how galaxies rotate, how fast the stars whirl around the centre, and how galaxies move within clusters, the numbers do not add up. There is not nearly enough visible matter, not enough stars and gas, to hold these things together with gravity. They should be flying apart, they are not. So there must be additional mass, unseen mass, providing the extra gravity. We call it dark matter, and it makes up roughly 27% of the total content of the universe, more than 5 times as much as all the ordinary matter, all the stars and planets and gas and dust and people combined. And we do not know what it is. The leading guess is some undiscovered particle. But another possibility, the one Carr and Hawking opened, is that some or all of it is made of primordial black holes, invisible relics of the first instant, threaded invisibly through every galaxy. For decades, certain mass ranges for these objects were ruled out by careful observation, but the windows keep partly reopening. As recently as 2024, a study in a major astronomy journal argued that the way we calculate black hole evaporation breaks down in the final stages once a black hole has lost about half its mass, and that this reopens a window at very low masses for primordial black holes to still be around as dark matter. The point is not the technical detail. The point is that after 50 years, we still cannot close the case. We cannot say primordial black holes definitely exist, and we cannot say they definitely do not. They sit in that uncomfortable, fertile gap between confirmed and excluded, and there are hints, tantalizing and inconclusive. A long-running survey called OGLE, which watches for the gravitational lensing flicker when a dark object passes in front of a distant star, has caught events consistent with compact objects of around 5 times the mass of the Sun that show no sign of any star attached to them, which is exactly what a free-floating black hole with no stellar history would produce. The LIGO gravitational-wave detectors have recorded black hole collisions involving objects whose masses are awkward to explain through the normal life and death of stars, and some researchers have wondered aloud whether those too might be primordial. None of it is proof. But the candidate list is not shrinking, it is growing. Now here is what makes a primordial black hole genuinely different from every star-born black hole, and genuinely more unsettling. A normal black hole has a history. It formed from a specific star, in a specific place, and often left behind a nebula, a scattering of debris, a signature we can find. A primordial black hole has none of that. No stellar remnant, no nebula, no predictable location. It could be anywhere, because it was not born from anything we can trace. And a small one, we are talking about something with the mass of a large asteroid compressed into a point smaller than an atom, could pass straight through a planet and leave only the faintest gravitational whisper, a subtle seismic tremor that we would almost certainly file under some other, more ordinary cause. There is no monitoring network watching for primordial black holes passing through the Earth. There is no catalogue of where they are. If one went through, we would most likely never know, or we would find out only afterward by examining the wreckage. That phrase is going to come back tonight, so let me say it plainly now. With the things on this list, over and over, we would know only by the wake. Not by seeing the thing itself, which gives off no light and hides from every instrument, but by seeing the disturbance it leaves behind. That is how you hunt the invisible. You do not look for the object, you look for the hole it leaves in everything around it. And I want you to sit for a moment with what the dark matter possibility really means, because this is the point where a statistic turns into something you can feel. If dark matter is primordial black holes, or even if it is some undiscovered particle, the conclusion is the same and it is genuinely strange. The galaxy you live in, the Milky Way, the great wheel of stars you belong to, is mostly made of something you have never seen and could never touch. The stars, all those hundreds of billions of stars, are not the galaxy. They are the glowing minority riding inside a much larger invisible structure, a halo of dark matter that outweighs them several times over and that we detect only by its gravity. You're not living in a galaxy of stars with some dark matter mixed in. You're living inside an invisible scaffold that happens to have some stars caught in it. You are a visible thing, made of the rare 5% that shines, embedded in a universe that is overwhelmingly structurally permanently invisible to you. And some of that invisible material may be relics of the first instant of creation, ancient beyond all reckoning, with no fixed address, moving silently through everything, recognizable only by the wreckage they leave behind. It helps to picture just how small and how dense some of these objects would be, because it is the compression that makes them so hard to find. A primordial black hole with the mass of a large asteroid, something you might think of as a modest lump of rock a few kilometers across, would be crushed by its own primordial origin into a point smaller than a single atom. All that mass folded into a region so tiny that it could pass through solid matter, the way a bullet passes through fog, interacting with almost nothing, tugging faintly on what it passes but touching nothing directly. It would not glow. It would not collide in any ordinary sense. It would slide through a planet, through a star, through you, and leave behind only the faintest gravitational disturbance, a whisper of tidal stress along its path that we would almost certainly never recognize for what it was. This is the difference between hiding and being invisible. A rogue planet hides because it gives off no light. A small primordial black hole is invisible in a more fundamental way, because there is almost nothing you could do to make it announce itself. The story of trying to pin these objects down is a long tug-of-war between hope and constraint. For every mass range where someone proposed that primordial black holes could be the dark matter, someone else found an observation that seemed to rule it out. If they were common at certain masses, they would bend the light of distant stars too often, and we do not see that. If they were common at other masses, they would have disrupted things we can measure, and they have not. Over the decades, the allowed windows kept narrowing, and many physicists came to think the idea was mostly dead. And then, again and again, a new analysis reopens a window that was thought closed, the way that 2024 study did by questioning how black holes evaporate in their final stages. That is the honest, unfinished shape of the science. Not a clean yes, not a clean no, but a 50-year argument that keeps refusing to resolve, precisely because the objects in question are so good at not being found. And whether or not dark matter turns out to be primordial black holes specifically, the larger fact stands, and it is one of the strangest facts in all of science. There is more than 5 times as much dark matter in the universe as there is ordinary matter, and we have never held a piece of it, never captured a particle of it, never directly detected it in any laboratory, despite decades of increasingly sensitive experiments built for exactly that purpose. We know it is there only by its gravity, by the way galaxies spin and clusters hold together and light bends around invisible mass. We live pressed up against the single largest category of stuff in the universe, and it passes through us constantly, and we cannot feel it, and we do not know what it is. The universe, in other words, may have seeded itself with countless invisible black holes in its very first moment, and then spent 13 billion years hiding them in plain sight. But at least a black hole, primordial or not, is made of ordinary collapsed matter, the same protons and neutrons as everything else, just crushed. The next thing on the list may not be ordinary matter at all. It may be a truer, more stable form of matter than the kind you're made of, and if a single stable seed of it exists anywhere, the danger is not that it explodes. The danger is that it touches you. Everything you have ever touched is made of ordinary matter. Atoms with nuclei built from protons and neutrons, and those in turn built from the two lightest kinds of quark, the up quark and the down quark. This is the matter of your body, your chair, the earth, the sun, the stars. It feels like the only kind of matter there is, the default, the bedrock. And for a long time, physicists assumed it was also the most stable kind, the lowest and most settled state that matter could fall into. In 1971, a physicist named Arnold Bodmer questioned that assumption, and in 1984 Edward Witten, one of the most respected theoretical physicists alive, developed it into an idea that is quietly one of the most disturbing in modern physics. What if ordinary matter is not the true ground state? What if there is a form of matter that is even more stable, even more settled, lower in energy than the atoms you're made of, and the only reason you have never seen it is that the universe has not, in your neighbourhood, found its way down into it yet? The candidate is called strange matter, and the name comes from a third kind of quark, heavier than the up and the down, called the strange quark. Witten's conjecture was that matter made of roughly equal parts up, down, and strange quarks, all packed together, might be more stable than ordinary nuclear matter. The reasoning is subtle, but the intuition is graspable. Quarks are the kind of particle that resist being crowded together, and having three different types to work with, rather than just two, gives them more room to arrange themselves at lower energy. If that is correct, then a lump of strange matter, once formed, would not want to fall apart. It would be the most stable material in the universe, more stable than the iron at the Earth's core, more stable than anything. A small lump of this material has a name. It is called a strangelet, and here is where the idea stops being an abstract curiosity and starts being the stuff of quiet nightmares. Because if strange matter really is more stable than ordinary matter, then contact between the two would not be a peaceful meeting. It would be a conversion. An ordinary nucleus touching a stable strangelet would find a lower energy state available to it, the strange matter state, and physics is relentless about rolling downhill into lower energy. The ordinary nucleus would convert. It would become strange matter, and in doing so it would release energy and grow the strangelet slightly, so that it could touch and convert the next nucleus, and the next. The process, in principle, would be self-sustaining, a chain reaction, spreading outward, turning ordinary matter into strange matter as it went. Let me make this concrete, and then, because it matters, let me pull the fear back down. Imagine you are holding an ordinary iron nail, cold, grey, unremarkable, the most boring object in the room. Now imagine that a single stable strangelet, a speck far too small to see, comes to rest against the very tip of it and touches one atom. There is no bang, there is no flash. That is the strange and awful part. What begins is not an explosion, it is a conversion, a silent front moving down the length of the nail, atom by atom, the ordinary iron reorganizing itself into strange matter as the front passes through, and the nail growing colder and denser and heavier in your hand second by second without a sound. Not an explosion, a change. That is the signature of this particular horror, and it is worse than an explosion precisely because it is so quiet. An explosion warns you. A conversion just arrives. Now let me keep my promise and pull it back to the ground, because the honest science here is genuinely reassuring, and it would be a cheap trick to leave you with only the nightmare. This scenario has been taken seriously enough to study carefully, and every direct search has come up empty. Physicists have hunted for strangelets at particle colliders at the accelerator complex at Brookhaven, in an experiment called NA52 at CERN, and with the star detector at the relativistic heavy ion collider. Every search has returned nothing. When that collider first switched on at the turn of the millennium, some people worried aloud that smashing heavy nuclei together at high energy might create a dangerous strangelet, and the concern was studied in detail by teams of physicists, and their conclusion was firm. Beyond reasonable doubt, they said, these experiments will not endanger the planet. The argument that settles it is beautiful in its simplicity. Cosmic rays, particles from space, have been slamming into the moon and into the Earth and into everything in the solar system at energies far higher than any collider can reach for more than 4 billion years. If dangerous strangelets could be made that way, they would have been made countless times already, and the moon would not still be there. The moon is still there, so the mechanism does not work the way the nightmare requires. But, and this is the reason strangelets are on this list rather than filed under solved, the theory cannot be completely closed. Whether stable strange matter can exist at all depends on quantities we have not fully pinned down, the precise mass of the strange quark, the fine details of how the strong force behaves in these conditions. The empty-handed searches at colliders are genuinely reassuring, but they are not the same as a proof that stable strange matter cannot exist anywhere in the universe. It might exist, for instance, far down in the crushing pressure at the cores of certain neutron stars, in objects that some physicists call strange stars, where the density is high enough to force matter into forms we cannot make on Earth. And this is where I want to be honest about the shape of the fear, because it is the same shape we will meet again at the very top of this list. In physics, the statement we have never detected it, and the statement it cannot exist are not the same statement. They are separated by a gap, and that gap is where the unease lives. We have never found a stable strangelet. We have very good empirical reasons, 4 billion years of undisturbed cosmic ray bombardment, to think that if they exist they are not the runaway planet-eaters of the nightmare. But we have not proven they cannot exist in some form, somewhere, under conditions we cannot reproduce. There may be a form of matter more stable than the atoms you're made of, quietly sitting at the bottom of a well that ordinary matter has simply never rolled into in your part of the universe yet. The most likely place for stable strange matter to actually exist, if it exists anywhere, is a place we have already learned to fear for other reasons, the core of a neutron star. When a massive star dies and its core collapses, it can be crushed into an object only about 20 kilometers across but heavier than the Sun, so dense that a single teaspoon of its material would weigh as much as a mountain range. Inside that crushing environment, matter is squeezed into states we cannot reproduce anywhere on Earth, and some physicists have argued that at the very center of some neutron stars the pressure could be high enough to convert ordinary matter into strange matter, producing what they call a strange star, a star made partly or entirely of the more stable quark matter that Witten imagined. If that is right, then strange matter is not merely hypothetical. It is sitting, sealed under unimaginable pressure, at the hearts of dead stars scattered across the galaxy. And every so often 2 neutron stars collide, and in that collision, some have wondered, fragments of strange matter might be flung out into space, small seeds drifting away from the wreckage. Whether any such seed could survive, and whether it would be stable enough to be dangerous, nobody knows. That is precisely the gap. I keep returning to that gap because it is the honest heart of this entry, and because it teaches something about how science actually handles the unknown. When the relativistic heavy ion collider was about to switch on at the turn of the millennium, the strangely worry was serious enough that physicists wrote careful public reviews addressing it, and the same happened again years later before the Large Hadron Collider began operating. In both cases, the conclusion was reassuring and well-reasoned, resting mostly on that beautiful cosmic ray argument, the fact that nature has been running these same collisions at far higher energies throughout the solar system for over 4 billion years without ever triggering a runaway. That is genuinely strong evidence, and I do not want you to lie awake over strangelets. But notice the exact shape of what was concluded. The reviews did not prove that stable strange matter is impossible. They proved that if it can be made this way, it would already have been made, and since we are still here, this particular pathway is safe. That is a statement about a mechanism, not a statement about existence. Stable strange matter, in some form, under some conditions we cannot reach, remains an open theoretical possibility, and the searches that have come up empty narrow the question without ever fully closing it. That distance between we have never found it and it cannot exist is going to matter enormously at the very top of this list, so hold on to the feeling of it now, at small scale, where it is safe to examine. It is the feeling of a door that science has been unable to either walk through or lock. Most of the time, an unlocked door leads nowhere. but you cannot prove it leads nowhere simply by never having gone through it, and that irreducible uncertainty, that thin permanent maybe, is the exact texture of the most fundamental fear on this entire list. That is the smallest hidden thing on this list, a speck that could, in the most extreme version of the theory, rewrite matter by touch. We have now looked at 5 of these lurking things, and I want to stop for just a moment before we go on, because a pattern has been forming, and I think it is worth naming out loud before we start climbing toward the truly large end of this list. We're halfway down the list, so let us stop and put the pieces together, because if you have been drifting, this is the moment to gently reset, and if you have been following closely, I think you have already started to feel the shape of the thing. Look back at the 5 we have covered: rogue planets, drifting unlit between the stars, invisible because they shine with no light of their own; interstellar visitors, crossing through our solar system and detected only as they leave; primordial black holes, relics of the first instant with no address, betrayed if at all only by their gravity; strangelets, a form of matter we have never held, that might not exist at all, or might be sitting at the bottom of an energy well waiting. And in every single case, the thing that unites them is not what they are. It is what they are not. They are not visible. That is the whole pattern. Every one of these is defined by the fact that we cannot see it directly, that it hides in the space we call empty, that we know it, when we know it at all, only by its effects, only by the wake. That is worth sitting with, because it means the fear we have been circling is not really a fear of any one of these objects. A rogue planet is not going to hurt you. An interstellar comet is a marvel, not a threat. The runaway conversion of the strangelets nightmare is, by the best evidence we have, something the universe already tested 4 billion years ago and shrugged off. Taken one at a time, none of these should keep you awake. The unease comes from the pattern behind them, the growing realization that the calm, empty, finished sky is a story your eyes tell you, and the real universe underneath that story is enormous, active, and overwhelmingly hidden. The dark is not empty, it is full, and we are only able to point at the small handful of full things that happen to leave a trace we can catch. Notice something else about the order we have been travelling in. We started with things you could almost touch, worlds with surfaces, objects with edges. Then we moved to things with no surface at all, black holes that are just curved space, matter that is only theoretical. The list has been quietly climbing a ladder, not of danger exactly, but of scale and strangeness, moving away from objects and towards something more fundamental, and that climb is about to get much steeper. Because everything in the first half of this list was in some sense a thing sitting inside space. A world, a visitor, a relic, a lump. From here on, the hidden things stop being objects in space and start being properties of space. The second half of this list is where we leave behind anything you could ever stand on or fly past, and start dealing with the invisible on a scale that makes a rogue planet look cozy and local. We are going to meet a monster the size of a galaxy's core that has been thrown clean out of its home and is tearing through the emptiness between galaxies. We are going to meet a sound that fills all of space at once, made by the largest objects in the universe, a sound so low that only a detector the size of the galaxy could ever hear it. We are going to meet a cold mark in the oldest light in existence that our best theories cannot fully explain. We are going to meet a region of nothing so large that it is pushing our entire galaxy across the universe. And then we are going to meet the 2 at the top, the ones that are not objects at all, the invisible majority of everything, and the quiet possibility that space itself is not what it appears to be. I told you at the start that the last thing on this list is not an object. I am still not going to tell you what it is, but I will tell you that everything from here down is preparation for it, each rung teaching your intuition to accept a little more, so that when we finally arrive at number 1, you will be ready to feel the full weight of it, instead of just hearing the words. There is also a shift happening in how these things could ever hurt anything, and it is worth naming, because it is part of why the list is ordered the way it is. The first 5 were, in their different ways, local and physical. A rogue planet is a place. A comet is a lump. A primordial black hole, if it exists, is a compact object with a location. A strangelet, in the nightmare version, is a seed that spreads by contact. These are the kinds of danger our intuition is built for, things with edges that move from here to there. But the second half of the list leaves that behind. You cannot be struck by a void the way you could be struck by a comet. You cannot be reached by dark energy the way a strangely reaches matter by touch. The things at the top of this list do not threaten you as objects at all. They reshape the stage the objects sit on. They are dangers, or mysteries, of a completely different category, and part of what the second half asks of you is to let go of the idea that the scariest thing must be a thing that can hit you. Sometimes the scariest thing is the floor, and keep hold of one phrase as we climb, because it is going to keep proving true at every scale. We would know only by the wake. We met it first with a primordial black hole, a whisper we would probably miss. We are about to meet it with a runaway monster, a wake 200,000 light-years long. We will meet it with a void, found only because everything flees it, and finally with the largest force in the universe, known only by the flight of the galaxies. The same lesson, over and over, growing each time. You do not find the hidden things by seeing them. You find them by seeing what they do to everything else. So take a breath, get comfortable again. We are done with the things you could bump into. From here the things get larger than worlds, larger than stars, larger, in the end, than the universe we can see. And the first of them is a single object so heavy that its home should never have been able to let go of it, and yet somehow it did, and now it is loose. At the centre of almost every large galaxy sits a supermassive black hole. Ours has one. It is called Sagittarius A star. It weighs about 4 million times the mass of the Sun, and it sits at the exact centre of the Milky Way, anchored there, the still point around which the whole wheel of stars turns. That is the normal arrangement. Supermassive black holes live at the hearts of galaxies. They are the anchors, the foundations, the heaviest single things a galaxy possesses, and they stay put. The idea of one wandering loose, out on its own in the emptiness between galaxies, is not supposed to be part of the picture at all. In 2023, a team led by the Yale astronomer Peter van Dokkum was looking at a Hubble Space Telescope image of a distant galaxy when they noticed something that did not fit. A thin, straight streak of light, razor-sharp, extending out from the galaxy into empty space. It was so narrow and so unusual that at first it looked like a flaw in the image, a cosmic ray hit or a scratch. It was not. When they studied it, they arrived at an interpretation that, if it holds, describes one of the strangest objects ever found. The streak, they proposed, was the trail of a runaway supermassive black hole. Here is the picture they assembled. A supermassive black hole, weighing around 20 million times the mass of the Sun, had somehow been ejected from its galaxy and was now racing through intergalactic space at roughly 1,000 kilometers every second. That is about 3.5 million kilometers per hour, and behind it, stretching back toward the galaxy it had left, was a trail of newly formed stars about 200,000 light-years long. To put that length in perspective, that trail is about twice the diameter of our entire Milky Way galaxy. A single object, dragging a wake of new stars twice as wide as the galaxy you live in. Think about how that wake forms, because it is the opposite of what you would expect. You might imagine a runaway black hole devouring everything in its path, a cosmic mouth eating its way across space. That is not what is happening. Instead, as the black hole ploughs through the thin gas that fills intergalactic space, it compresses that gas in front of and behind it, and compressed gas collapses and ignites into new stars. So the monster is not leaving a trail of destruction. It is leaving a trail of creation, a 200,000 light-year corridor of newborn suns lit up in its wake, marking the path of something you cannot see. Because you cannot see the black hole itself. It gives off no light. You see only the stars it has kindled behind it, the glowing signature of an invisible thing passing through. There is that phrase again, and it has grown since we first met it. We would know only by the wake. With a primordial black hole, the wake was a faint seismic whisper we might never catch. Here, the wake is 200,000 light-years of new stars, a scar of light across the dark drawn by an object we can only infer. Same principle, unthinkably larger scale. The invisible thing announces itself not by what it is, but by what it disturbs. How do you throw a 20 million solar mass black hole out of a galaxy? You do not do it gently. The favoured explanation is a kind of gravitational slingshot, a chaotic three-body interaction. When galaxies merge, their central black holes sink toward the middle and can end up in a tangled dance of 2 or even 3 supermassive black holes at once. And a three-body gravitational encounter is famously unstable. It can fling one of the participants away at enormous speed, the same way a spacecraft can steal energy from a planet in a slingshot maneuver. Except here the object being flung weighs 20 million suns. The math works. Mergers happen constantly across cosmic history, and the leftover, in this rare case, is a homeless monster moving fast enough to escape its galaxy entirely. Now, in the spirit of honesty that this whole list depends on, I have to tell you that this interpretation is debated. Science is not a single voice, and a good strange claim invites careful pushback. Since the original discovery, other researchers have argued that the observations could also be explained by something much more ordinary, an edge-on view of a normal star-forming galaxy that only looks like a trail because of the angle we happen to see it from. That debate is still live. It may turn out that RBH1, as the object has been nicknamed, is not a runaway black hole at all. But here is why it earns its place regardless of how that particular argument resolves. The physics that would produce a runaway supermassive black hole, the three-body ejection during galaxy mergers, is real and well understood, and galaxy mergers are common. Whether or not this specific streak is the real thing, the mechanism that would make such objects exists, which means they should be out there, somewhere, whether we have correctly identified one yet or not. And that is the quietly disturbing takeaway. We tell ourselves a comforting story about supermassive black holes. We say they are anchored, foundational, safely parked at the centres of galaxies where they belong. This object, if it is what it appears to be, says that story is not always true. The heaviest single things in the universe are not guaranteed to stay home. At least one of them appears to have been thrown out of its own galaxy and is now crossing the void, trailing a wake of new stars twice the width of the Milky Way. And we found it only because a sharp-eyed astronomer noticed a streak that looked like a scratch. The horror here is not that one is aimed at us. Intergalactic space is so enormous that the odds of any such encounter are essentially nothing. The horror is smaller and stranger than that. It is that objects of this scale, objects heavier than the hearts of galaxies, can be loose, can be homeless, can be moving, and can be, until the exact moment their weight catches the light, completely invisible. Let me give you a sense of the violence required to make this happen, because it is easy to say slingshot and miss how extreme the physics really is. Our own central black hole, Sagittarius A star, weighs about 4 million suns, and it would take an almost inconceivable event to shift it, let alone launch it out of the galaxy. The runaway object is roughly 5 times heavier than that, around 20 million suns, and it is moving at about 1,000 kilometers a second. To throw an object that heavy that fast, you need one of the most extreme gravitational events the universe permits. The leading picture requires not 2 but 3 supermassive black holes to end up close together, which happens when galaxies that each already had a central black hole merge, and then a third arrives from yet another merger. When 3 objects that massive get into a tight gravitational dance, the arrangement is chaotic and unstable, and the most likely outcome is that 2 of them pair off tightly, while the third is flung away at enormous speed, carrying off the excess energy. It is the same physics that lets a small spacecraft steal a little speed by swinging past Jupiter, except scaled up until the projectile weighs 20 million suns, and the launch speed is 1,000 kilometers every second. Picture what that object looks like as it travels, because the geometry is part of what makes it so eerie. In front of it, where it plows into the thin intergalactic gas, there is a bow shock, a compressed leading edge like the wave pushed ahead of a ship's prow, except this prow is an invisible point of infinite density. Behind it stretches the 200,000 light-year wake of newborn stars, cooling and igniting in the disturbed gas the black hole leaves churning behind it. So you have a completely invisible object, betrayed at its front by a shock in the gas, and at its back by a corridor of fresh starlight longer than 2 Milky Ways laid end to end. You never see the thing. You see the disturbance it makes coming, and the disturbance it makes going, and from those 2 disturbances you infer a monster in between them that emits nothing at all. And I keep saying if it holds, because I want to be scrupulous, but let me be clear about why the entry survives even the strongest doubt. Suppose the skeptics are right, and this particular streak turns out to be an ordinary galaxy seen edge-on. That would settle one image. It would not touch the underlying physics, which says that galaxy mergers happen constantly across cosmic time, that many of those mergers involve multiple supermassive black holes, and that 3-body gravitational encounters can and do eject participants at high speed. those facts are not in dispute. Together they say that runaway supermassive black holes should exist somewhere, whether or not we have correctly identified our first one yet. The universe has the mechanism and the raw material. Somewhere out in the dark between the galaxies, the largest objects that exist are not all safely anchored where we expect them to be, and at least some fraction of them are loose and moving and dark. A runaway black hole is at least a single thing, moving through a single place. The next item on the list is not in any one place. The next item is everywhere at once. It is a sound of a kind, and it is filling all of space around you right now, and it is made by objects exactly like this one, the largest black holes in the universe, in the act of finding each other. In June of 2023, a collaboration of astronomers called Nanograv, working alongside partner teams in Europe, China, India and Australia, announced that they had detected something that had been passing through the Earth and through you and through everything for the entire history of the human species, completely unnoticed. They had detected a hum, a low, continuous background of gravitational waves filling all of space at a pitch so low that the word pitch barely applies. To understand what they found, you have to understand what a gravitational wave is. When massive objects accelerate, especially when they orbit each other, they send ripples through the fabric of space itself, actual stretching and squeezing of distance, spreading outward at the speed of light. Einstein predicted them more than a century ago. In 2015, the LIGO detectors caught the first one directly, a sharp chirp from two stellar mass black holes spiraling together and colliding in a fraction of a second. That was a single event, brief and loud, one pair of black holes finishing their dance in an instant. What Nanograv found is not a single event. It is the opposite of a single event. It is a constant droning background, a superposition of countless sources all sounding at once, and it comes from the largest black holes in the universe. Supermassive black holes, the kind that anchor galaxies, the kind we just watched go runaway in pairs, spiraling slowly toward each other after their galaxies have merged. Each such pair over millions of years stirs space with gravitational waves of enormous wavelength, waves that take years or even decades to complete a single cycle, waves whose crests are measured not in meters but in light years. And there are so many of these pairs scattered across the universe, so many merged galaxies with their central monsters slowly circling, that all their waves overlap into one continuous background, a sea of ripples that never stops. How do you detect a wave whose wavelength is measured in light years? You cannot build a detector big enough. So the astronomers used a detector that already existed, one the size of the galaxy. They used pulsars. Pulsars are the spinning corpses of massive stars, and they sweep beams of radiation past the Earth with astonishing regularity, ticking like cosmic clocks, some of them more precise than anything humans have built. Nanograv spent 15 years watching dozens of these pulsars scattered across the sky, timing their ticks to fantastic precision, looking for a very particular pattern. If a background of gravitational waves is passing through the galaxy, it should very slightly stretch and squeeze the distances between us and each pulsar, subtly shifting the arrival time of their ticks, and, crucially, the shifts for pulsars in different parts of the sky should be correlated in a specific mathematical pattern predicted decades ago. After 15 years of watching, the pattern emerged. The evidence favoured a real gravitational wave background over mere random noise by an enormous margin, a confidence factor larger than 10 followed by 14 zeros. Space, they concluded, is ringing. Let me try to put you inside it, because this one is almost impossible to picture and worth the effort. You are floating in the emptiness between galaxies, far from any star, in what looks like the most perfect stillness imaginable. Nothing to see, nothing to hear, because there is no air and in the ordinary sense there is no sound at all. And yet the space around you is not still. It is breathing. The gravitational wave background is passing through you, through the region you occupy, stretching and compressing the very distances around your body by an almost inconceivably tiny amount. You cannot feel it. Nothing can feel it directly. But if you could watch the distance between yourself and a pulsar many light years away, and if you were patient enough to watch for years, you would see that distance slowly breathe, lengthening and shortening by about the width of a single molecule in and out on a rhythm that takes years to complete. It is a sound too immense and too slow for any ear, a note so low that a single beat of it outlasts a human life, and it is playing everywhere, all the time, and it has been playing through the earth since long before there was an earth. And when you ask what is making that sound, the answer is the reason this belongs on a list of things lurking in the dark. The hum is, most likely, the summed voice of every supermassive black hole pair in the observable universe, all of them spiraling toward collision at once, their individual songs blurred together into one endless chord. Individually, these black holes weigh from 100 million to 10 billion times the mass of the Sun. Collectively, their slow-motion mergers fill all of space with a vibration we are only now, after 15 years of listening, able to confirm is there. The largest, heaviest, most violent processes in the universe, and they announce themselves not with a bang but with a drone so quiet and so low that we needed a galaxy-sized instrument and 15 years of patience just to be sure it existed. I should be honest that the interpretation, while strongly favoured, is not the only one on the table. The amplitude and shape of the background match what we expect from supermassive black hole pairs very well. But some physicists have noted that a portion of the signal could, in principle, come from more exotic sources in the very early universe, relics of cosmic strings or of violent phase transitions in the first instance after the Big Bang. Either way, the conclusion is the same, and it is humbling. Space itself is vibrating at a frequency far below anything we could have imagined listening for, and the silence we always assumed was out there, the perfect quiet of the void, was never silence at all. It was a sound we simply could not hear. I want to dwell on the instrument itself for a moment, because it is one of the most quietly beautiful ideas in modern astronomy. The pulsars that nanograv uses are not ordinary. They are millisecond pulsars, dead stars spinning hundreds of times every second, and the beams they sweep past us arrive with a regularity that rivals the best atomic clocks humans have ever built. A pulsar might send a pulse toward Earth every few thousandths of a second, and it will keep that beat so faithfully that astronomers can predict the arrival of a given pulse years in advance to within a fraction of a millionth of a second. That precision is the whole trick. If space between us and the pulsar stretches or squeezes, even by an amount smaller than the width of a molecule spread across light years, the pulse arrives a hair early or a hair late. No single pulsar could prove a gravitational wave background this way, because a lone late pulse could mean anything. But if you watch dozens of pulsars scattered all over the sky, and you find that their timing shifts are correlated in the exact geometric pattern that a passing sea of gravitational waves would produce, the pattern named for the physicists Hellings and Downs who predicted it decades ago, then you have caught the background. 15 years of watching, dozens of the most precise natural clocks in the galaxy, all shimmering together in the predicted way. That is what it took, and the timescales involved are almost impossible to hold in the mind. LIGO's detections are quick, violent and human-scaled in a sense, a chirp lasting a fraction of a second as two ordinary black holes finish their spiral. The waves nanograv found are the opposite in every dimension. Their wavelengths are measured in light years. A single one of these waves can take years, even decades, to complete one full oscillation, one slow breath of stretching and compressing space. These are not events. They are a permanent condition of the universe, a background drone that has been sounding since long before the Earth formed and will keep sounding long after it is gone. When you hear that space is ringing, do not picture a bell struck once. Picture a note so low and so sustained that a single cycle of it is longer than the entire history of human civilization, playing continuously, everywhere, made by the slow orbital dance of the heaviest objects the universe contains. There is something almost tender in the fact that we can hear it at all. For the whole history of our species, this background was passing through every person who ever lived, stretching the ground beneath them by amounts too small to imagine, and no one knew. It took the invention of radio astronomy, the discovery of pulsars, the recognition that some of them tick with clock-like precision, and then 15 patient years of timing them, before we could finally confirm that the silence had a sound in it after all. We did not make the universe quieter or louder. We simply, finally, learned to hear a note that had been playing the entire time. That is the thing about this entire list, said in a new way. Silence was never silence. Emptiness was never emptiness. The stillness of the night sky is the stillness of a room whose lowest sound is pitched too low for your ears, in which enormous things are happening that you were never equipped to notice, and we have now climbed high enough that the hidden things are no longer objects at all. This last one was a vibration filling all of space. The next one is a stain in the oldest thing there is, a cold mark left on the very first light the universe ever released, and after more than 20 years we still cannot fully explain how it got there. The oldest thing you can see is light. Not a star, not a galaxy, but a faint glow that comes from every direction in the sky at once, the thermal afterglow of the Big Bang itself. It is called the cosmic microwave background, and it is a kind of photograph of the universe as it was about 380,000 years after the beginning, at the moment the cooling cosmos first became transparent and let its light travel free. That light has been travelling ever since, for more than 13 billion years, and it is still arriving, faint and cold, filling the whole sky. It is the closest thing we have to a baby picture of everything, and the remarkable thing about that baby picture is how smooth it is. The temperature of this ancient glow is almost perfectly uniform across the entire sky, the same in every direction to within tiny fractions of a degree. Those minuscule variations, the places that are the barest sliver warmer or cooler than average, are the seeds of everything, the faint unevenness from which galaxies and clusters would eventually grow. Cosmologists have mapped these ripples in exquisite detail, and for the most part they follow the predictions of the standard model of cosmology beautifully, a statistically smooth, even, well-behaved sky. But in the first year of data from NASA's WMAP satellite, released in 2003, there was a region that did not behave. In the direction of the constellation Eridanus, there was a patch of sky that was measurably significantly colder than everything around it, about 70 millionths of a degree below the average. That sounds like nothing, and in absolute terms it is a tiny number, but against the extraordinary smoothness of the rest of the sky, it stood out immediately, a cold blemish where the standard model expected nothing special. It was confirmed later by Europe's Planck satellite, so it was not an instrument error. It was really there. It became known, simply and ominously, as the cold spot. The problem is its size and its depth together. The cold spot spans something on the order of 1 billion light-years across the sky, and a cold region that large and that cold is hard to produce by ordinary random chance in the standard model. It sits right at the edge of what statistics will comfortably allow, the kind of feature that makes cosmologists uneasy, because either it is a genuine fluke, an unlucky roll of the cosmic dice, or it is telling us that something is there that our models did not include. The leading conventional explanation is called a supervoid. The idea is that between us and that patch of the ancient light lies an immense, underdense region of space, a place with far fewer galaxies than average, called the Eridanus supervoid. When the light of the cosmic microwave background passes through such a giant emptiness on its long journey to us, it can lose a little energy, cooling very slightly, through a subtle effect tied to the expansion of the universe as the light crosses the void. In December of 2021, a team using the Dark Energy Survey strengthened the case, finding a real correlation between the location of the supervoid and the location of the cold spot. So part of the mystery does seem to be a genuine giant emptiness lying in that direction, another one of these enormous invisible voids that we will meet again in just a moment. But here is the catch, and it is why the cold spot is still on a list of unexplained things rather than filed under solved. When you do the arithmetic, the supervoid can account for only part of the temperature deficit. It cools the light a little, but not by as much as we observe. There is a residual, a leftover coldness that the supervoid explanation does not fully cover, so even the best conventional answer leaves a gap, and into that gap, over the years, more radical proposals have crept. The most provocative of these comes from the physicist Laura Massini-Houghton, and it is the kind of idea that sounds like science fiction, until you remember that a serious cosmologist proposed it in the scientific literature. Her suggestion is that the cold spot could be a bruise, specifically the imprint left on our universe by a collision with another universe, during the earliest moments of cosmic inflation, when, in some models, our universe was one bubble among many, springing into existence alongside others. If our bubble brushed against a neighbouring bubble universe in that first instant, the contact could have left a mark, a faint scar pressed into the oldest light, a cold patch that would be, quite literally, the fingerprint of another universe touching ours. I want to be very clear about the status of that idea, because this is exactly the kind of claim that gets stripped of its caveats and turned into a headline. The multiverse collision interpretation is controversial. Most cosmologists do not accept it. It is a minority view, a speculative reading of an anomaly that most researchers think will eventually be explained by a supervoid plus perhaps a little statistical bad luck. But, and this is the honest part, it has not been formally ruled out. The cold spot remains genuinely unexplained at the level of full detail. Whether it is a supervoid, a fluke, or the print of a neighbouring cosmos is, at this moment, an open question, and I would be lying to you if I pretended science had closed it. Set aside the wildest interpretation, though, and the plain facts are strange enough. The oldest light in existence, the afterglow of creation, the most carefully studied signal in all of cosmology, carries a cold mark that our best models cannot fully explain. A blemish printed onto the first thing the universe ever released, sitting there in the data for more than 20 years, most likely a giant emptiness, possibly a statistical accident, and just possibly something far stranger pressing against the boundary of everything we can see. It is a reminder that even the beginning of time, the part of the universe we think we understand best, has a mark on it we cannot read. It is worth understanding why a supervoid would cool the light at all, because the mechanism is subtle, and it depends on the very thing we will meet at number 2. When a beam of ancient light falls into a large region of a lower density, it has to climb down into the region's shallow gravitational well and then climb back out the far side. In a universe that was not expanding, those two climbs would cancel perfectly, and the light would emerge with exactly the energy it entered with. But our universe is expanding, and the expansion is accelerating, so during the long time it takes the light to cross a region 1 billion light-years wide, the gravitational well itself flattens out beneath it. The light does not have to climb back out of as steep a well as it fell into, and so it comes out having lost a little energy, slightly cooler than it went in. That effect, named the integrated Sachs-Wolf effect, is real, it is measurable, and the Dark Energy Survey confirmed that the Eridanus supervoid and the cold spot really do line up in the way this mechanism predicts. So part of the answer is solid. The trouble, again, is that solid part is not big enough. When cosmologists carefully calculate how much cooling the supervoid should produce through this mechanism, they get a number smaller than the coldness we actually observe. The void explains some of the cold spot, perhaps a meaningful fraction of it, but not all, and that leftover, that stubborn residual coldness, is what keeps the anomaly alive. You're left with a choice between two uncomfortable options. Either the cold spot is partly a statistical fluke, an unlucky roll that happened to land on top of a real supervoid, which is possible but feels like leaning hard on coincidence, or there is something in that patch of the early universe that our standard picture does not contain. Neither option is comfortable, and that discomfort is exactly why the more radical ideas have room to breathe. I keep coming back to how strange it is that the anomaly sits in the oldest light of all. This is not some distant galaxy we're puzzling over. This is the afterglow of the beginning itself, the most ancient and most carefully mapped signal in existence, studied by 2 separate satellites over more than 20 years, and it has a mark on it that our best theory of the early universe cannot fully account for. Whether that mark is a giant emptiness, a statistical accident, or, in the reading most cosmologists doubt but cannot entirely dismiss, the faint print of another universe that once touched ours, the honest answer today is that we do not know. The beginning of time, the part of the cosmos we often assume we understand best, carries a blemish we have not managed to read. And notice how that explanation kept leaning on something we have not yet properly confronted, a giant region of nothing, an emptiness so large it can leave a cold shadow on the light of creation. That brings us to number 3, because it turns out that emptiness on the larger scales is not a passive gap in the universe. It is an active force, and there is one particular region of nothing so immense and so empty that it is pushing our entire galaxy across the cosmos right now. You're moving right now, faster than you have ever let yourself imagine. Not just the spin of the Earth, not just the Earth's orbit around the Sun, not just the Sun's long circuit around the centre of the galaxy. Beyond all of those, the entire Milky Way and our whole neighbourhood of galaxies, the group astronomers call the local group, is hurtling through the universe at about 630 kilometres every second. That is more than 2 million kilometres per hour. We measured it against the cosmic microwave background, that ancient light we just discussed, which acts as a kind of universal reference frame, and there is no doubt about the number. We are being carried across the cosmos at a speed that would take you from the Earth to the Moon in about 10 minutes, and we cannot feel a thing. For a long time we knew we were moving, but did not fully understand why. There was an obvious suspect. In one direction lies an enormous concentration of galaxies, a great overdense region called the Shapley concentration, and it made sense that its gravity was pulling us toward it, the way a stone rolls downhill toward the heaviest mass. That was half the answer, but only half. Because when astronomers led by Yehuda Hoffman carefully mapped the three-dimensional flow of thousands of galaxies in our part of the universe in 2017, they found that the pull of Shapley was not enough on its own to explain our motion. Something else was contributing from the opposite direction, and when they looked at that opposite direction they found nothing, and the nothing was the point. In the direction we are fleeing from, they discovered a previously unknown, very large region that is almost completely empty of galaxies. They named it the dipole repeller, and the name captures exactly what it does. It repels. Our local group is not only being pulled toward the crowded Shapley concentration on one side, it is also being pushed away from this immense emptiness on the other, and the two effects, the pull from the full region and the push from the empty one, turn out to be of roughly comparable importance. Half of our headlong rush across the universe is us falling toward something. The other half is us fleeing from nothing. Now, I have to be careful with the word push, because a region of emptiness cannot literally reach out and shove anything. There is nothing there to do the shoving. That is the whole point of a void. So how does nothing push? The answer is one of those ideas that is simple once it clicks and strange forever after. Gravity is not really about being pulled toward mass. It is about the competition between all the masses tugging on you from every direction at once. Normally those tugs come from all sides and roughly cancel out. But if there is a great emptiness on one side of you, then on that side there is very little mass, and therefore very little pull. Everything else, all the ordinary matter on the other sides, wins the tug of war. And so you drift away from the emptiness, falling toward the fuller side of the sky, as surely as if the emptiness had reached out and pushed you. The void does not push. It simply fails to pull, and in a universe governed by the balance of gravity, failing to pull is functionally the same as pushing. Sit with what that means for a moment. Our entire galaxy, everything we are and everything we can see from here, is being steered across the universe at 2 million kilometers an hour, partly by a region so empty and so immense that it exerts almost no gravity at all. We are being moved by an absence, and that absence was invisible to us for the entire history of astronomy, because how do you see a region defined by having nothing in it? You cannot photograph a void. It emits no light because it contains almost nothing that could. The only way Hoffman's team found it was indirectly, by mapping the motion of thousands of galaxies and noticing that they were all, collectively, flowing away from one particular patch of sky, all running from the same nothing. They inferred a giant feature of the local universe purely from the shape of a cosmic drift, purely from the wake, once again, of a thing that cannot be seen. This is worth letting reshape your sense of what the universe is made of structurally. We tend to picture the cosmos as galaxies scattered through empty space, with the galaxies being the important part and the space being the boring background. The dipole repeller says we have it backward. The large-scale structure of the universe is a web, filaments and sheets and walls of galaxies wrapped around enormous voids, and those voids are not passive gaps. They are active players. They shape the motion of everything around them by the gravity they fail to exert. The emptiness is not the stage on which the drama happens. The emptiness is one of the actors, and in our own case, it is currently steering the galaxy we live in. There is something almost vertiginous about that once it lands. You're not sitting still on a quiet Earth under a fixed sky. You're riding a galaxy that is being flung across the universe by the combined influence of a distant crowd of galaxies you will never reach, and a nearby ocean of nothing you can never see. Both of them invisible to you. Both of them enormous beyond any human sense of scale. And your entire experience of a calm, stationary night is possible only because the motion is so smooth and so immense and so far beyond the reach of your senses that you were never built to notice it at all. To understand how anyone could map a thing made of nothing, you have to picture the method, which is a genuine feat of cosmic cartography. Hoffman and his colleagues did not photograph the void because there was nothing to photograph. Instead, they gathered the measured velocities of thousands upon thousands of galaxies across a huge region of the local universe, building a three-dimensional map not of where galaxies are but of how they are moving. And when you map motion rather than position, the hidden architecture reveals itself. The galaxies trace out great streaming rivers of flow, all of them draining on one side toward the dense regions and all of them fleeing on the other side from a single patch of sky where the flows diverge as if repelled. That diverging patch, the place everything is running from, had to contain almost nothing, because only an absence of gravity could make galaxies flee it in every direction. They found the void not by seeing it, but by watching everything around it run away and drawing the shape of the emptiness from the shape of the flight. This same technique, mapping the flows, is what let astronomers redraw our cosmic address entirely. It turns out our galaxy sits at the outer edge of an enormous connected basin of flowing galaxies, a supercluster so large it was given its own name, Laniakea, a Hawaiian word meaning immense heaven, spanning something like 500 million light-years. We are not at its centre, we are near its thinning edge, and part of what defines that basin is the great emptiness pushing from beyond it. So your cosmic home address, fully written out, includes not just a planet and a star and a galaxy and a local group, but a position on the slope of a supercluster, tilted by the pull of a distant crowd of galaxies and the push of a nearby ocean of nothing, both of them far too large and too faint to ever see. I find something genuinely vertiginous in holding all of that at once, and I think it is worth letting yourself feel it rather than filing it away. You're not sitting still. You're riding a planet, around a star, around a galaxy, that is itself being flung across the universe at 2 million kilometers an hour. And the thing doing half of the flinging is a region so empty and so enormous that it exerts almost no gravity at all, and could only be found by the shape of everyone running from it. Your entire lived experience of a calm and stationary night, a fixed earth under a still sky, is possible only because the motion is so immense, so smooth, and so utterly beyond the scale of your senses that you were never built to notice you were moving at all. We have now reached the point where the hidden things are no longer things at all, in any ordinary sense. A void is not an object, a hum is not an object. And the last two items on this list, the two at the very top, are the least object-like of all, and the most important. Because everything we have discussed so far, every world and visitor and relic and monster and void, adds up, in the end, to a tiny fraction of what the universe actually is. The overwhelming majority of everything is still ahead of us, and it is number 2, and we cannot see it, cannot sample it, and cannot explain it, even though it makes up most of reality, and it has already decided how the universe ends. In 1998, 2 competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Notice the assumption buried in that sentence. Everyone knew the universe was expanding, and everyone assumed that the expansion had to be slowing, because gravity pulls, and all the matter in the universe should be tugging everything back together, gradually applying the brakes to the cosmic expansion. The only question, they thought, was how hard the brakes were being applied. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, and both were using a particular kind of exploding star, a Type 1 supernova, as a cosmic measuring stick, because these explosions all shine with nearly the same true brightness, so their apparent brightness tells you exactly how far away they are. Both teams found the same thing, and it was the opposite of what they expected. The expansion of the universe was not slowing down. It was speeding up. Something was pushing everything apart, overpowering the collective gravity of all the matter in the cosmos, and it was getting stronger over time, not weaker. The discovery was so unexpected and so well established that it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it opened a wound in physics that has never closed. We gave the thing doing the pushing a name, and the name is really just a label for our ignorance. We call it dark energy. And here is the number that should stop you. Dark energy makes up about 68% of the total energy content of the universe. Add in dark matter, the invisible mass we discussed earlier, at about 27%, and you find that ordinary matter, everything made of atoms, every star and planet and galaxy and living thing, every object in this entire list except the last 2, adds up to roughly 5% of what exists. 5%. The universe is, to a first approximation, made of 2 things we cannot see and do not understand, and the small bright remainder, the part we can actually study, is a rounding error riding on top. So what is dark energy? The honest answer is that we do not know, and it is worse than simply not knowing, because our best attempt to calculate it produces what may be the most embarrassing failure in the history of science. The simplest idea is that dark energy is the energy of empty space itself, a fixed energy that every cubic centimetre of vacuum possesses just by existing, what physicists call the cosmological constant. Quantum theory should be able to predict how much energy empty space contains. When physicists actually do that calculation, they get a number that is too large compared to what we observe, by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is not a small error. It is not a factor we are close on. It is the two most successful theories in all of physics, quantum mechanics and general relativity, disagreeing about the energy of empty space by the largest margin of disagreement that has ever appeared anywhere in science, and we have no idea why the real value is so small, why it is not enormous, and why it is not simply zero. For a long time, most physicists assumed dark energy was that cosmological constant, fixed and unchanging, the same energy density of empty space for all of cosmic history. It was the simplest assumption, and simple assumptions are usually a good bet. But the universe may be about to take that comfort away. There is an instrument called DESI, the Dark Energy Spectroscopic Instrument, which is building the largest three-dimensional map of the universe ever made, measuring the positions of millions of galaxies and quasars across billions of years of cosmic time. And when DESI released its second major batch of results in March of 2025, drawing on about 14 million galaxies and quasars gathered over 3 years, the data pointed somewhere unsettling. It hinted that dark energy is not constant after all, that its strength may be changing over cosmic time. When the DESI data was combined with other measurements, the preference for a changing, evolving dark energy over a fixed one reached a statistical confidence of about 4.2 sigma, which in plain terms means a chance of something like 1 in tens of thousands that it is a random fluke. I have to be careful and fair here, the way the DESI collaboration itself has been careful and fair. This is a hint, not a verdict. 4.2 sigma is strong, and it is getting stronger with each data release, but extraordinary claims in cosmology demand extraordinary confirmation, and the researchers themselves stress that more data is needed before anyone declares the cosmological constant dead. But the direction of the signal is not toward the comfortable answer. It is toward a dark energy that lives and changes, and if that is confirmed, it would break the simplest model of the universe and reopen questions about the long-term fate of everything that we thought had been settled. And while the physicists argue over the decimal places, the thing itself keeps working silently everywhere all the time. Let me tell you what dark energy is actually doing to the sky, because this is where the statistic becomes something you can feel. Every galaxy outside our own local group is accelerating away from us, and because that acceleration keeps increasing, there will come a time, far in the future, when those galaxies are receding so fast that their light can no longer reach us at all. They will cross what is called the cosmic horizon and become permanently invisible, permanently unreachable, gone not because they were destroyed, but because the space between us stretched too fast for any signal to ever cross it again. The universe is not just expanding, it is being emptied. One galaxy, one horizon at a time, the neighbours are being carried out of view forever by a force we cannot name. There is a quiet grief in that, once you let it land. Far in the future, any astronomers who exist will look out and see only their own galaxy, alone in a black and empty sky, with no evidence that any other galaxy ever existed, no way even to discover the expanding universe we take for granted, because all the evidence will have receded beyond reach. We happen to live early enough in the history of the universe to still see the other galaxies, to still have the neighbours in view. We are witnesses to a scene that is slowly, permanently closing, and the thing closing it is invisible, unexplained, and possibly getting stronger. Once again, and for the last time before the end, we know the largest force in the universe only by the wake it leaves, the great outward flight of every galaxy we can see, drawn by something we have never detected and cannot describe. Let me sit with that 10 to the power of 120 for one more moment, because it is easy to say a big number and hard to feel it. When two theories in physics disagree, we usually argue about the second or third decimal place. A disagreement of a factor of 10 would be a serious crisis. A factor of 100 would be a scandal. This is a disagreement of a 1 followed by 120 zeros. There are only about 10 to the power of 80 atoms in the entire observable universe, so the mismatch between what quantum theory predicts for the energy of empty space and what we actually measure is vastly larger than the number of atoms in existence. It is not that we are a little bit wrong about dark energy. It is that our two greatest theories, the quantum description of the very small and Einstein's description of the very large, when asked the same simple question, what is the energy of empty space, hand back answers so far apart that the gap between them is larger than almost any number that appears anywhere else in science. An empty space is not some exotic edge case. It is the most common thing there is. We do not understand the energy of nothing, and nothing is most of everything. The instrument now pushing on all of this, DESI, deserves a picture too, because it is measuring the history of the universe by measuring its shape over time. It sits on a telescope in Arizona, and it captures the light of thousands of galaxies at once, thread by thread, building a three-dimensional map that reaches back billions of years. By measuring how galaxies are clustered at different distances, and therefore at different ages of the universe, DESI can trace how fast the universe was expanding at each stage, and from that, how the strength of dark energy has behaved across cosmic time. That is what makes its recent results so provocative. If dark energy were a true cosmological constant, its strength would be identical at every stage, flat, unchanging, forever. The data instead leans, at a confidence of about 4 in 100,000 of being a fluke, toward a dark energy whose strength has shifted over time. It is a hint, not a proof, and the scientists themselves keep saying so. But it is a hint that the simplest story is wrong, and that the force emptying the universe is not a fixed feature of space, but something that lives and changes. And through all of that argument over decimals and models, the effect keeps quietly working, which brings back the phrase that has followed us all night. We cannot see dark energy. We have never captured it, never sampled it, never detected it in any way except one. We know it only by the wake, by the great outward flight of every distant galaxy, accelerating away, drawn apart by something we cannot name. It is the same lesson as the primordial black hole and the runaway monster and the pushing void, arrived at now on the largest possible scale. The most important actors in the universe are invisible, and we know them only by the disturbance they leave in the things we can see. Except here the disturbance is not a seismic tremor, or a trail of stars, or a diverging flow. Here the disturbance is the fate of everything, the slow, permanent emptying of the sky. 68% of everything is a stranger. It is invisible, it is unexplained, it may be changing, and it has already decided how the universe ends, whether or not we ever learn what it is. And you would think that would be the most frightening thing a list like this could offer, the discovery that most of reality is a force we cannot see steering the cosmos toward an empty ending. But it is only number 2, because dark energy, whatever it is at least a feature within space, a property of the vacuum doing something. Number 1 reaches further than that. Number 1 is not something hiding in space, or something filling space, or something moving space. Number 1 is the possibility that space itself, the vacuum, the empty stage on which all of this happens, is not what it appears to be, and never was. On the 4th of July, 2012, physicists at CERN announced that they had found the Higgs boson, the last missing piece of the standard model of particle physics, a particle that had been predicted nearly 50 years earlier and hunted ever since. It was one of the great triumphs of modern science, the completion of a picture that describes every known particle and force except gravity. There were tears and champagne, and buried inside that triumph was a number that a certain kind of physicist had been quietly hoping would come out differently, because the value of that number placed our entire universe in a position that is difficult to describe as anything other than precarious. The number was the mass of the Higgs boson, and it came out to about 125 in the units physicists use. That value, when you feed it into the equations, places the universe in what is called a metastable state. And to understand what metastable means, and why it is the most unsettling word on this entire list, you need one simple picture. Imagine a ball resting in a small dip partway down the side of a hill. The ball is at rest, it looks stable, it could sit there apparently forever. But it is not at the bottom of the hill. There is a lower place it could reach, a lower valley further down, and the only thing keeping the ball in its little dip is a small ridge, a barrier holding it in place. That ball is in a metastable state, stable enough to sit still, but not truly at the lowest point available to it. Given enough time, or the right disturbance, it could cross the barrier and roll down into the lower valley. and when physicists measured the mass of the Higgs and worked through the consequences, in calculations led by Giuseppe de Grassi and his colleagues that same year, they concluded that the vacuum of our universe, the ground state of empty space itself, is very likely that ball. Not at the true bottom, resting in a dip with a lower valley somewhere below it, held in place by a barrier that has lasted so far but that may not last forever. The empty space around you, in other words, may be a false vacuum. It looks like nothing. It looks like the most stable, most settled, most finished thing there could possibly be, the very definition of at rest. But it may not be at its lowest energy. There may be a truer vacuum, a lower valley, and if any patch of space anywhere ever found its way across the barrier and dropped into that lower state, the consequences would be beyond anything else on this list. Here is what would happen. A tiny bubble of true vacuum would form, would nucleate, at some point in space. And because the true vacuum is a lower energy state, that bubble would immediately begin to grow, its wall expanding outward in every direction at nearly the speed of light. Inside the bubble, the constants of physics would be different. The strength of the forces, the masses of the particles, the rules that let atoms exist, all of it would be rewritten. Atoms as we know them almost certainly could not exist inside the bubble. Everything the true vacuum swept over would simply cease to be the kind of thing it had been. And because the bubble wall travels at essentially the speed of light, nothing could outrun it, and nothing could warn of it. No light, no signal, no information of any kind could arrive ahead of the wall, because the wall moves as fast as any warning possibly could. The bubble's arrival and the end of physics as we know it, in that region, would be the same instant. There would be no flash to see, no sound to hear, no moment of realizing it had come. You would not experience the end. There would simply and completely be no more you, and no more of the physics that made you all at once with no before and after, because there would be no one left on the other side to mark the difference. Do you hear the shape of that? It is a horror we already met small near the middle of this list and now returned at the largest possible scale. It is not an explosion. It is a change. The strangelet converted matter by touch, a silent front moving through a nail. Vacuum decay converts reality itself, a silent front moving through space, rewriting the rules as it goes. The smallest hidden thing on this list and the largest turn out to be the same kind of thing, the same quiet, total, unstoppable conversion, differing only in what they convert, and that is why number one is not an object. You cannot point at it. It is not lurking in space. It is the possible state of space, the ground floor of reality, which may not be the true ground floor. Now I have to keep the most important promise of the whole night, which is the promise to be honest, because the honesty is what turns this from a cheap scare into something worth your time. Here is the crucial fact. The estimated lifetime of our metastable vacuum, the expected time before it would spontaneously decay, is almost unimaginably long. Not billions of years, not trillions. The estimates run to something like 10 to the power of 100 years, a one followed by 100 zeros, a span of time so much longer than the current age of the universe, which is a mere 13.8 billion years, that the comparison barely means anything. The universe as it stands is a newborn by this clock. Most physicists regard the near-term risk as, for all practical purposes, exactly zero. And there are respectable ideas in physics beyond the standard model that would restore true stability and remove the possibility altogether, so please do not carry this to bed as a fear. Carry it as something stranger, and I think more beautiful. Because the point of putting vacuum decay at number one was never the probability. It was the character of the thing, and what it reveals about where we live. Every other item on this list was hidden inside the universe. This one is a property of the universe, our own best measurements, the crowning achievement of the standard model, the Higgs boson we were so proud to find, quietly told us that the stillest, safest seeming thing in all of existence, empty space, the calm dark itself, may not be in its final form. The vacuum may be resting in a dip on the side of a hill, on a clock so long we will never see it move, but resting there all the same. The ultimate hidden thing lurking in the dark is not a monster in the dark. It is the dark. It is the quiet possibility that reality itself is not yet finished settling. The idea itself is older than the Higgs measurement, which is part of why the measurement landed the way it did. Physicists had understood the mathematics of a decaying false vacuum for decades, worked out in careful detail in the 1970s, long before anyone could say whether it applied to our universe. They knew in theory how a bubble of true vacuum would form and grow, how the barrier would be crossed by quantum tunneling, the same ghostly process that lets particles pass through walls they classically could not climb. What they did not know was where our universe actually sat, whether it was truly stable, truly unstable, or balanced in that in-between metastable state. The answer depended on a few numbers we had not yet measured precisely, and the most important of them was the mass of the Higgs boson. So when CERN finally pinned that mass down in 2012, it did not just complete the standard model, it also, quietly, dropped our universe onto a specific point on that stability map, and the point it landed on was not the safe one. It landed in the metastable region, the ball in the dip on the side of the hill. I want to be precise about the strangeness of the timescale, because it is where the fear and the comfort live side by side. When physicists estimate how long a metastable vacuum like ours would take to decay on its own, they get numbers like 10 to the power of 100 years, sometimes far longer. Set that beside the age of the universe, 13.8 billion years, which is a mere 10-digit number, and the comparison collapses into meaninglessness. If the lifetime of the vacuum were a single year, the entire history of the universe so far would have taken up less than the first blink of the first second. On that clock, everything that has ever happened, every star, every galaxy, all of cosmic history is an event so early and so brief it has barely begun. The vacuum is not decaying on any timescale that touches us, or our descendants, or our galaxy, or in all likelihood the era of stars itself. That is the comfort, and it is real, and I mean it. The fear is not about when. It is about what the mere possibility says regarding where we are standing. The safest, stillest, most finished-seeming thing in all of existence, the empty vacuum, the calm dark, may be resting on a slope rather than sitting at the bottom of the valley, held in place by a barrier on a clock we can barely write down. And there is no way, even in principle, to look at a region of space and confirm it is truly stable, because a false vacuum and a true one look identical from the inside, right up until the instant they do not. So let me bring you all the way back to where we started, and let me give you the sky again, because you see it differently now. You're looking up at the same calm night sky from the beginning of all this. The same black field, the same scatter of fixed points, the same backdrop that felt so finished and so empty. But you cannot see it as empty anymore, because now you know what fills it. Out there in the dark between the stars are billions of unlit worlds, drifting with no sun, some of them perhaps warm inside. Passing through your own solar system unannounced are visitors from other stars, and you will never know when the next one slips by. Threaded invisibly through your galaxy are relics of the first instant of creation, and an invisible scaffold of dark matter that outweighs every star you can see. Somewhere out there a monster the mass of 20 million suns is running loose, trailing a wake of new stars. All of space around you is humming, right now, with a sound too low to hear, made by the largest black holes in the universe finding each other. The oldest light carries a mark we cannot read. Your whole galaxy is being pushed across the cosmos by a great emptiness. Most of everything is a force we cannot name, quietly carrying the other galaxies out of view forever. And beneath all of it, holding all of it up, is a vacuum that may itself be waiting on an almost endless clock to change. Notice, as you take that in, that the two ends of this list have quietly folded together. Number 7, the strangelet, was the smallest thing we discussed, a speck that could convert matter by touch, not with an explosion but with a change. Number 1, the vacuum, is the largest possible thing, the state of space itself, and it too would spread not as an explosion but as a change, a silent front rewriting reality as it passed. The smallest hidden danger and the largest turned out to share a single shape. And running between them, connecting every rung, was that other phrase, the one about the wake, the recognition that we never see these things directly and only ever know them by the disturbance they leave in what we can see. A tremor, a trail of stars, a diverging flow of galaxies, the flight of the whole visible universe, different disturbances, different scales, one method. That is what it means to read the dark. The dark is not empty, it is full. That is the one thing I most wanted you to feel tonight, and I hope it has stopped being a sentence and become something you can sense when you look up. But here is the turn, the thing I want to leave you with instead of dread. Every single one of these hidden things, The invisible worlds, the passing visitors, the ancient relics, the loose monster, the humming background, the cold mark, the pushing void, the unseen majority, the possibly unfinished vacuum, every one of them was found or inferred or taken seriously by us. By a temporary fragile visible arrangement of that rare 5% of matter that happens to shine. By creatures who evolved to catch a thin ribbon of light, and who somehow from inside a mostly invisible universe, with senses tuned to almost none of it, worked out what was hiding in the dark. We cannot see dark matter, and we found it anyway. We cannot hear the gravitational-wave background, and we listened for it anyway, with a detector the size of the galaxy. We cannot watch a false vacuum, and we deduced its existence from the mass of a single particle. That is the strange comfort at the bottom of all of this. The floor was never as solid as it felt. The sky was never as empty as it looked. And yet here we are, briefly, able to know it, able to sit in the dark and correctly imagine what the dark contains. The universe spent 13 billion years hiding almost everything it is made of, and a species that has been looking up for only a few thousand years has already found the edges of most of it. So the next time you look up at that calm, quiet, finished-looking sky, I hope you feel the fullness of it, all of it, the worlds and the monsters and the voids and the unfinished vacuum underneath. And I hope the feeling that reaches you is not fear, but the quiet astonishment of being one of the few things in the universe that can look into the dark and begin to see.